This is the fourth and final part in a series of videos that introduce the Urantia Book's unorthodox and unexpected cosmology. For those who haven't seen the previous parts, in the first we look at the Urantia Book's unique and completely new foundations for physics and see how so-called dark mass emerges from condensates of space potency. In the second, we put ultimatonic or axionic foundations under the standard model for particle physics and see why Dirac's model for the electron and a Higgs-type mechanism work so well. In the third, we look closely at what happens when the neutrons in a neutron star start to melt, and why so-called dark islands or Planck stars eventually tend to explode. For those who've seen these videos, I think you'd agree that the Urantia Book tells quite a tale about mass and matter and dark islands that explode. Central to this story are these new foundations for reservoirs of energy and invisible mass that science currently can measure but can't explain. This is especially relevant for astronomy, so in this final part I'd like to explore what these new foundations might mean for the Milky Way, our home sector in an ancient super-universe. We'll also see how these papers use cosmological redshift to tell a surprising story about the history and motions of space. However, before we begin, I should mention that the authors themselves throw cold water over our expectations. From Paper 101, Section 4, quote, "Within a few short years, many of our statements regarding the physical sciences will stand in need of revision." End quote. Will stand in need of revision. These papers were written in 1934, and clearly many of their, quote, "statements regarding the physical sciences simply echo scientific ideas of the day." But later, in that same section, the author makes a list of things that, as revelators, they were permitted to do. And anyone who reads this section will have to wonder which of their more interesting scientific statements represent, quote, "authoritative elimination of error," or, quote, "otherwise earned knowledge." These are significant carrots they left dangling, the possibility for authoritative elimination of error and for the revelation of otherwise earned knowledge. In other words, when exploring these papers, we should be on the lookout for 1. Hints about where native physics has gone wrong, and 2. Insight about things beyond human capacity to prove, and thus possibly otherwise earned. And something else to keep in mind. The authors of the Urantia Book view the cosmos from outside time, which means they can say some interesting things about eternal purposes and transcendental causation, and even about Einstein's spooky action at a distance. But this also means that any sequential, time-dependent history they reveal must involve ambiguities and compromise. Nevertheless, they explain that reality really does involve a crucial finite phase of time-dependent evolution. It's this finite or time-dependent side of Urantia Book cosmology that we'll explore. Okay. In telling their time-dependent story of the cosmos, the authors distinguish between two distinct components. One is ancient, organized, and small. The other is impressively vast and possibly quite young. This small part they call the grand universe, a massive disk-like structure at the center of enormous nested levels of outer space. Taken together, these two components, this ancient tiny kernel and these vast levels of outer space, form the so-called master universe. This distinction between an ancient, organized grand universe and unevolved levels of outer space is so unorthodox that our first step is really just to get a feel for the sort of story the Urantia Book reveals, and to see if it's compatible with what astronomers actually observe. Here's the plan. We'll begin with the birth of spiral galaxies and consider a neat solution to the mystery of invisible or dark mass. Next, we'll review what we actually know about our place in space and see how the Urantia Book's grand universe might fit into this astronomical context. Regarding the Milky Way and what the authors call a superuniverse, in particular the superuniverse of Orvonton, we'll compare what astronomers actually see with what the papers seem to say. One thing we'll find is that the story of Orvonton involves an awful lot of time, much more than 14 billion years, so we'll also explore how a simple idea about redshift has led cosmologists to believe in a young universe beginning with a hot Big Bang. First, spiral galaxies and invisible mass. In 1934, the authors of the Urantia Book described how spiral galaxies evolve in massive, invisible, superfluid disks of axion-like prions, and how these massive, invisible disks emerge from halos of primitive force charge, and how these halos of charge are condensed from a global potential. These axion-like prions they call ultimatons. This halo of primitive, weak hypercharge they call segregata, and this global potential pervading all space they call absoluta, or space potency. In this scheme, the story of galaxies begins with this halo of segregata, the segregation of an island of primitive, primordial, weak hypercharge, what nowadays we'd call a locally localized Higgs-type field. From within this field, a disk of ultimatons appears, invisible, massive, superfluid, and it's from within this disk that spirals of stars emerge. They're atoms, they're leptons and quarks, built up from clusters of these axion-like ultimatons, as we saw in Part 4b. Regarding mass, in these papers, the so-called mature ultimaton is described as, quote, the first measurable form of energy. They also refer to segregata as, quote, pure energy. So this halo plus disk, this halo of segregata plus disk of ultimata, represent an awful lot of energy. But following Einstein, if we divide all this energy by the speed of light squared, then what we also have is an awful lot of mass, or rather an awful lot of invisible gravitational effect. Regarding gravity, these authors make a surprising distinction between two very different types. One type of gravity they call local or linear, a kind of quantizable gravitational charge, which appears wherever leptons and quarks and atoms begin to form. The other type of gravity they call absolute, a nonlinear, time-transcending global grasp on energy of all forms. To make sense of so-called gravity, we'd have to accommodate both types. So, in 1934, at the very same time Fritz Zwicky first noticed the need for invisible mass, 40 years before, Vera Rubin measured those flat rotation curves of spiral galaxies. The authors of the Urantia Book presented, or predicted, exactly the sort of model that researchers have recently begun to explore. A model that assumes, or predicted, the sort of Higgs-type field our standard models require. in 1934. Okay, so these papers say something interesting about how spiral galaxies form. What about on a larger scale? For example, do they say anything interesting about this? This clip from a video by Brent Tully's group, part of their Cosmic Flows project, shows the distribution of superclusters centered on our region of space out to about 250 million light-years, or 75 megaparsecs. Our Milky Way sits at the center of this flow, near the Virgo cluster, in a region of surprisingly empty space, the so-called local void. In this simulation, Tully's group have tried to do three things. First, account for all the normal matter our telescopes can find. Next, estimate an associated distribution of invisible or dark mass. And finally, extrapolate the motion, the so-called cosmic flow, of all this mass, given their predicted distribution and using some old assumptions about gravity and space. Now, allowing for some confusion in Tully's map about what's actually flowing where, the Urantia Book predicted in 1934 that we would find a distribution something like this, a void or quiescent region of almost empty space, ringed by great walls of clusters of galaxies. It also predicted, in 1934, that as we mapped this ring, we would indeed confirm a local, outwards Hubble flow, because for the past 500 million years, space has been expanding. But they added a twist, claiming that beyond this ring, beyond, say, 100 megaparsecs, about 320 million light-years, redshift becomes not so much a reliable indicator of distance, but more a source of increasing confusion the further out we look. And they added another twist. Not only is this ring of superclusters expanding, along with all of space, they claim it's also rotating about a center very close to where we are, here near the Virgo cluster. But this is not just another rotating cosmology. These authors go on to describe a set of far more distant and far larger counter-rotating flows, as well as global cycles of expansion and contraction, a kind of gentle respiration of all space, all of which goes against the grain of current cosmological assumptions, especially this idea about the universe having a center. Of course, if the universe really does have a center, then some of those current cosmological assumptions would need to change. So before we explore the dynamics of deep space and see why beyond a certain distance the usefulness of redshift begins to fail, and why our Type 1a supernova data seem to fit best within 100 megaparsecs, let's first zoom in closer to home into the center of this cosmic flow. First, to see what astronomers have actually discovered, and second, to explore what sort of center these Urantia Book authors propose. Here's a rough redshift plot of the region where Tully's group are mapping those cosmic flows. Virgo, our local supercluster, is in the center. Zooming in, we find the local sheet, a thin sheet of galaxies sandwiched above and below by so-called voids, huge bubbles of apparently empty space. We're here in the middle of this sheet within the so-called local group. Zooming in a little more, here's a map of this local sheet, about 40 million light-years across. The local group, with our Milky Way, is here in the center. In 2014, astronomer Marshall McCall presented a study of this region, carefully remapping all bright galaxies within 20 million light-years of the Milky Way. And this is what he found, an apparent ring of 12 large galaxies to which he gave the catchy name, a Council of Giants. Andromeda and the Milky Way are near the middle of this ring, just off-center. And let's add in those invisible halos of segregata and disks of superfluid ultimata. The surprise here, and the point of McCall's paper, is that relative to each other, these 12 giant galaxies seem to be bound together, as if holding formation in this persistent elliptical ring. Now, to native astronomers, this Council of Giants is just one of those things, a chance arrangement due to gravity. But in the Urantia Book scheme, it may be something more. In fact, the Urantia Book has a lot to say about this region of space. But first, I should mention a mystery. Until recently, astronomers assumed that the giant Andromeda galaxy, with its trillion stars and enormous diameter, must be much more massive than our Milky Way. But recent studies of the dwarf satellites of both suggest that the Milky Way actually might weigh more, or rather that some system containing our Milky Way has some unexpected gravitational effect. Hold that thought. So this is the sort of neighbourhood astronomy reveals. Now, here's the question. Does the Urantia Book add anything worthwhile to this picture? Can the Urantia Book story of an organised centre surrounded by nested, counter-rotating cosmic flows be made to fit? Let's see. Paper 15 begins by revealing that our Milky Way spiral sits out towards the rim of, quote, one gigantic wheel, that inhabited superuniverse domains lie within this wheel, and that Andromeda sits just outside, cruising along this, quote, ragged edge. One feature of this wheel is that it's pervaded by, quote, primordial force charge, what nowadays we'd call a condensate of weak hypercharge, or locally localized Higgs-type field. But primordial force charge is also called segregata, or pure energy. So once again, if we divide all this energy by the speed of light squared, then what we have here is an awful lot of mass, or rather gravitational effect, which would explain why Andromeda is falling in. Another feature of this wheel is that it's rotating relative to what they call the source and centre of universe gravity. This peculiar and absolutely unique arrangement makes possible a type of engineering that would have made Einstein and Carl Sagan smile. The use of Weyl curvature from tidal forces acting on space and time to shape 7 spokes for this grand universe wheel. Okay, given this, quote, first post-Havona space level, with its 7 spokes sweeping along the superuniverse rim of this grand universe wheel, time-dependent history quite literally begins, with 7 small teams of ancients of days stepping out from the eternal core of this grand universe wheel into its time-dependent rim. Paper 15 puts it like this, from paragraph 1, quote, thus constituting the vast creation one gigantic wheel, the hub being the eternal isle of paradise, the 7 spokes the radiations of the 7 master spirits, the rim the outer regions of the grand universe. End quote. The radiations of the 7 master spirits. What we have here are 7 flavours of energy and intent, adding characteristic colour to each superuniverse spoke in this grand universe wheel. Now, this is not the scientific method at work. This is simply one way to sketch the sort of centre the Urantia Book reveals. A centre for those nested, counter-rotating levels of outer space. A centre sufficient, eventually, to serve as capital for an absolutely ultimate master universe. Okay, the story so far. At the dawn of time, gravity helps to shape a disk of primordial hypercharge into 7 superuniverse domains. our own superuniverse, Orvonton, spanning 1/7 of the rim of this grand universe wheel. Our Milky Way just inside the inhabited domain, Andromeda just outside, one of those objects, quote, on the fringe of Orvonton and travelling along with us. And McCall's Council of Giants, his persistent elliptical ring, a boundary, the inner fringe of the first of those nested levels of outer space. For those wondering about the alignment of this grand universe wheel with respect to this local sheet, imagine a multi-gimbal gyroscope. For stability, I like to think of the outer space levels not only rotating around the grand universe, but also precessing over, reinforcing the idea of the grand universe as a stable central kernel for the future master universe. Of course, astronomers haven't found anything like this. But then again, there's a feature of this wheel we've not yet mentioned. It's very, very thin. Thin in the sense that the rings of Saturn are thin, forced by gravity and angular momentum into an almost two-dimensional plane. So thin that, when seen from the side, they almost disappear. Now, replace the gravity of Saturn with the source and centre of gravity. In this model, this grand universe wheel, shaped by the gravity of paradise, is about 10 million light-years across, but less than 10,000 light-years thick. That's a ratio of 1,000 to 1. In other words, this structure is Bible paper thin. As we'll see, this revelatory background allows us to tell an interesting tale about our ancient spiral sector of stars within our spoke in this grand universe wheel. But before we try to fit the Urantia Book's grand universe wheel into a modern cosmological frame, let's first look at what the scientific method has revealed. What do we actually know about the Milky Way? In 2010, National Geographic released a 2-hour documentary, Inside the Milky Way. This brought together everything we then knew and assumed about our home system of stars. To help set the scene, here's a 60-second clip from that documentary.
The Milky Way, we believe, is a spiral galaxy. So what we're really seeing when we look up at night at this band is we're seeing our place in the universe. We're part of a giant disk of stars.
But that's just an insider's view.
Now, of course, I can't show you a picture of the galaxy in all its glory. We can't fly above the galaxy and take a picture of it and show you. We're stuck in the disk of the galaxy. But we can still image it from the ground. In fact, this image is a picture of our galaxy, the Milky Way, taken from Earth. Perhaps the most beautiful part of this image is that we have this contrast of dark and light regions running through the plane of the disk. What that really is, it's dust. There are clouds of dust that are casting a shadow from the back of the stars. So the stars are trying to shine their light through. There are dust clouds there that are blocking the light, much like a cloud on Earth would block the sun.
About these clouds of dust and gas, what we see depends on how we look. When using visible light, we see something like this, which for poets or philosophers might be just fine. But for astronomers, it's just frustrating. Until recently, they had no way to see through all this dust and gas, so astronomers actually avoided looking at this entire part of the sky. Thus, for astronomers, this region became the zone of avoidance. But in 2003, NASA launched the Spitzer Space Telescope. And Spitzer was built to look in the infrared. In astronomy, what we see really does depend on how we look. And this is what we see when we look at that zone of avoidance in the infrared. Actually, this is the far infrared. Even better is the near infrared. At these wavelengths, 1 to 5 microns, all that cold dust and gas becomes transparent, and we get a better view of the actual distribution of stars. Now, we've known for some time that this belt of stars is at least 100,000 light-years wide. What's not so well known is the actual distribution of stars within this Milky Way, which turns out to be surprising. Astronomers now estimate that up to 95% of the Milky Way's hundreds of billions of stars lie in a thin disk less than 1,000 light-years thick. But 100,000 light-years wide by 1,000 light-years thick, that's the ratio of 100 to 1, like a DVD. So this disk is really, really thin. Okay, so what would this system look like from above? Here we have a problem. Astronomers have worked out that our Sun sits about 26,000 light-years from the centre of our spiral of stars. However, it's right in the middle of the dense mid-plane of the disk. And as James Bullock said, quote, "We can't just fly up above the disk to get a bird's-eye view. For us, trying to map the Milky Way is like a bit of pepperoni in a very, very big and very, very thin pizza, trying to map the pizza in which it's stuck, as astronomer Bob Kirshner explains."
It's something like a pizza, and if you were in the pizza, if you were a pepperoni, your view would not be a very clear one of what the whole story was. In the same way, we don't see the whole reach of the Milky Way.
What astronomers really need is a bird's eye view.
You would need to get out of the Milky Way to really see what it looks like. We don't have a way to do that, but we can look at other galaxies and see what they look like.
By looking at other galaxies, and by trying to map the Milky Way's spiral arms, astronomers now think that from above, the Milky Way would look something like this. Our Sun would be about here, and here's that centre of rotation, about 26,000 light-years away, we call Sagittarius a star. To estimate these distances, 26,000 light-years from the Sun to the centre, and 100,000 light-years wide, astronomers have a toolkit of techniques. Referring to this toolkit, in paper 41, section 3, the author states, quote, "By this technique," that's referring to Cepheid variables, "it's possible to measure stellar distances most precisely, up to more than 1 million light-years." End quote. Most precisely, up to more than 1 million light-years, which implies that our current measurements of distance within this disk are on track. In particular, this distance of 26,000 light-years to Sagittarius a star. Okay, so far, so good. Now, does the Urantia Book say anything interesting about this system of stars? Yes, it does. It says the centre of our so-called minor sector is over here. From paper 15, section 3, quote, "The rotational centre of your minor sector is situated far away in the enormous and dense star cloud of Sagittarius, around which your local universe and its associated creations all move." End quote. Now, if by star cloud of Sagittarius they mean Messier 24, about 11,000 light-years away, and if this dense star cloud is the centre of rotation for our minor sector, then Sagittarius a star, about 26,000 light-years away, becomes an obvious candidate for the centre of rotation of our major sector. Again, from paper 15, section 3, quote, "And from opposite sides of the vast Sagittarius subgalactic system, you may observe 2 great streams of star clouds, emerging in stupendous stellar coils." End quote. Notice, two great streams of star clouds. The authors connect our minor sector, Ensa, with a single star cloud, Messier 24, and then appear to suggest that the centre of our major sector, Splandon, lies somewhere between those streams of star clouds uncoiling from Sagittarius A star. And notice they call this entire spiral subgalactic. More on this soon. Now, all of this seems reasonable, but then they say something weird, or at least unexpected. From paper 32, section 2, quote, "From Gerusalem, the headquarters of Satania, it's over 200,000 light years to the physical centre of the superuniverse of Orvonton." End quote. 200,000 light years. That's another 174,000 light years past Sagittarius A star. In other words, way, way off to the right in this diagram. Remember, with regard to our astrometric toolkit, they said that we can measure such distances, quote, most precisely out to more than 1,000,000 light years. Let's try to put that distance in context. Once again from paper 32, section 2, quote, "From Gerusalem, the headquarters of Satania, it's over 200,000 light years to the physical centre of the superuniverse of Orvonton." And from the same paragraph, quote, "From the outermost system of inhabited worlds to the centre of the superuniverse is a trifle less than 250,000 light years." End quote. But hang on, in this story, Uversa is supposed to be a centre of rotation. A centre of rotation for, eventually, the 10 major sectors of a superuniverse. How can we make this work? Well, in that same section, the author also states that, quote, "Nebadon is now well out towards the edge of Orvonton." End quote. Here's that distance again, 250,000 light years from the edge of Orvonton to Uversa. But back in paper 15, section 3, they say that the length of this superuniverse is, quote, "far greater than the breadth." Do they mean something like this? And they reveal a bit more. From paper 15, section 3, paragraph 16, quote, "The local universes are in closer proximity as they approach Havona." End quote. They also state that on the Havona side, local universes are more tightly clustered and, quote, "layered." Are they suggesting a distribution something like this? But what about those 10 major sectors mentioned in paper 15, section 3, quote, "If you could look upon the superuniverse of Orvonton from a position far distant in space, you would immediately recognize the 10 major sectors of the 7th galaxy." End quote. About this term, 7th galaxy, throughout these papers, galaxy is used as a collective noun, as in galaxy of stars or galaxy of gods. So if we read galaxy as galaxy of major sector spirals, which we would immediately recognize, are they suggesting something like this? In the next paragraph, as we saw earlier, they refer to this major sector spiral, our Milky Way, as, quote, "subgalactic," which would make perfect sense if, when viewed, quote, "from a position far distant in space, Orvonton is seen to be a galaxy or collection of subgalactic major sector spirals." But then again, in paper 12, section 1, the author implies that this 7th galaxy of major sector spirals is, quote, "as yet uncompleted," end quote. Which makes you wonder, is the Andromeda spiral actually one of Orvonton's future major sectors, slowly sliding into place. Of course, nothing in native astronomy or cosmology predicts anything like this. But as a thought experiment, let's ask the question, if this spiral of stars were here, could we see it? Remember, almost all the Milky Way's hundreds of billions of stars lie along its mid-plane within this thin disk about 1,000 light-years thick. So in paper 32, where they mention that, quote, dense diameter of the Milky Way, think of this thin red band. Now, imagine we could bring that Andromeda spiral 10 times closer than it is and place it, say, 200,000 light-years behind the Milky Way. To get a better view, let's switch to infrared. Okay, if such a nearby giant spiral were spinning face-on to our line of sight, it would be very easy to see. But if we tilt this neighbour to be edge-on, its profile, in all wavelengths, becomes a faint echo of the foreground Milky Way. A faint echo. So when we drop it down into the plane of the Milky Way, its profile becomes, well, vanishingly faint. A vanishingly faint line, a smudge of black-body radiation sitting right behind that, quote, dense diameter of the Milky Way. So here's the question. Using existing telescopes, if such a neighbour existed, could we see it? Or what about this? A set of spiral galaxies. What we have here is a Urantia Book galaxy. In other words, a galaxy of major sector spirals, all tilted to be precisely edge-on, all lined up directly behind this dense diameter. The James Webb Space Telescope will be launched soon, and this is designed to look at the infrared, to cut through all that dust and gas. What if something like this, a galaxy of major sector spirals, were the first thing that telescope finds? Pause to consider. Keep in mind, this is still just our thought experiment. There's no scientific reason or data to suggest that a system like this exists. For me, this is just the simplest way to model what the papers seem to say. With this in mind, let's take the next step and see where this thought experiment leads. Clearly, a system like this implies architecture and organization, both of which the Urantia Book describes with its master architects and force organizers. And as we saw in previous videos, see parts 4a, b and c, these papers also provide the sort of extended standard physics that such a scheme requires, adding to this picture 3 essential but invisible or dark parts. 1, that vast, swirling cyclone of massive ultimata. 2, that ancestral halo of segregator or pure energy. And 3, and most importantly, the tidal effects of paradise, the universe's source and centre of gravity, acting for a very long time. Question is, could this sort of extended standard physics explain the evolution of a system like this? Let's have a look. Think how ice is less dense than water, how icebergs, enormous mountains of ice, float and get carried along by ocean currents. Now think of these spirals of stars, these disks of gravita, as icebergs in a flow, a vast superfluid flow, not of water, but of emergent ultimata. So these visible galaxies, these iceberg spirals, will naturally go with the flow, carried around Uversa, not just by gravity, but also by ancient, force-organized flows. Now, if we float this whole system in a cyclone of segregata, pure energy, then what we have here is a completely unexpected distribution of energy and mass, and thus gravitational action and response. Within such enormous energy-dense flows, these little spirals of stars would get carried along like so much fluff. The thing is, this sort of story fits right in with mainstream speculation. What we have here are spirals of stars evolving in dark, superfluid disks, nested in halos of some mysterious, invisible condensate, which is exactly the sort of thing that cosmologists right now are discussing at their conferences. So this sort of gravitational action on invisible mass is not so controversial. The real issues here are organization and time. Even with paradise architects and force organizers pulling the strings, it would take a long, long time to evolve a structure like this. And when we pop Orvonton into place as the seventh spoke in that grand universe wheel, this issue of time becomes deep in telling the story of this relatively small grand universe. The papers talk in terms of trillions with a T, not mere billions of years. Which raises an interesting point. In Urantia Book Cosmology, from a finite or time-dependent point of view, this grand universe age, this vast span of time and evolutionary effort, applies only along the super-universe rim of this grand universe wheel. The doings of outer space, relatively speaking, may have only just begun. Once again, let me emphasize, this is not the scientific method at work. This is simply a sketch of the sort of story the Urantia Book reveals, an attempt to see how our local spiral of stars, the Milky Way, might fit in with the idea of Orvonton, and how a truly ancient grand universe might fit into some kind of reasonable astronomical context. So now the fun begins. How do we connect up this handful of unorthodox and ambiguous ideas to what native science currently assumes? Let's have a look at what's involved. Mainstream cosmology currently sits on a few simple assumptions about Hubble's law, about redshift, and about the universe beginning with a hot Big Bang. Taken together, these ideas lead to models like so-called lambda CDM, and to predictions about the age and history of the universe. So where did all this come from? The idea of a Big Bang, these finely tuned models, these estimates of universe age? It began with the slope of this line. By 1929, astronomer Edwin Hubble had worked out rough estimates of distance to 24 nearby spiral galaxies. When he plotted these distances against redshift, he noticed that the distances to these spirals might be proportional to their redshift, which for astronomers would be huge. If true, they could find the distance to a galaxy just by reading its redshift. As to what was causing these redshifts, Hubble remained non-committal. Not so Georges Lemaitre. Lemaitre was another astronomer who jumped on Hubble's data as evidence that these spirals were all racing away, that their redshifts were a simple Doppler shift caused by their speed of recession. In fact, it was Lemaitre who first wrote down Hubble's law, assuming that the redshift of a galaxy reveals its velocity, and that velocity, the apparent speed of recession of spiral galaxies, is directly proportional to their distance, where the constant of proportion, Hubble's constant, or h0, is given by the slope of this line. Lemaitre's idea was that the entire universe must be expanding, as if growing from some original cosmic egg. Now, given that Lemaitre was a Catholic priest, and that his cosmic egg, this prototype Big Bang, was a bit too much like some creation myth, and that Hubble's data was a bit rough, many, including Einstein, thought that Hubble and Lemaitre had jumped the gun, that Hubble's so-called law was more leap of faith than real science. Nevertheless, by 1933, the very same time these papers were being presented, this idea about an expanding universe had caught on, and that the rate of this expansion is given by h0, again, the slope of this line. And sure enough, as the data improved, it really did look like Hubble and Lemaitre had been on the right track. As we can see from this recent plot, the data do seem to fit nicely with Hubble's original idea, that redshift might be proportional to distance. But notice, this is a plot of redshift versus distance. There's no mention of velocity. The idea that redshift is proportional to speed of recession or rate of separation is an assumption in a model, an assumption that cosmologists, like Lemaitre, have to add. But once we accept these assumptions and add a little fix near the start and another little fix near the end and calculate a so-called Hubble time, we get this story that cosmologists currently like to tell, which goes something like this. Given one miracle, one miraculous moment of cosmic inflation, and two little assumptions, we can predict that the universe began to expand about 13.8 billion years ago. About this story, there's a joke that physicists like to tell. Cosmologists are always wrong, but never in doubt. So, two little assumptions about redshift and rate of expansion, assumptions which nowadays seem so obviously true that some cosmologists no longer see them as assumptions, but rather as hard facts which their models must obey. It's no exaggeration to say that this story, this proposed expansion history of the universe, sits on these two assumptions. So in 2015, two physicists, not cosmologists, Harry Ringermacher and Lawrence Mead, took a close look at these assumptions and this story and the best data of the day, and they noticed something subtle in the supernova data, that the rate of change of the expansion has been changing every 2 billion years or so. They proposed that a simple Big Banged universe was in some sense ringing or oscillating as it expanded, that over the last 13 or 14 billion years, the rate of expansion of the universe has sped up and slowed down 6 or 7 times. The Urantia Book takes this unorthodox idea one more step. It proposes cycles 2 billion years long of gentle oscillation, of so-called space respiration. Paper 11, Section 6 discusses the idea. But getting back to the mainstream, this current consensus model, this assumed expansion history of the universe, is in effect defined by that Hubble parameter, h as a function of redshift or age, so predicting, or at least explaining its current value, h0, the rate of expansion now, has become a crucial test. Does this model really reflect universe history, or are we missing something? This is the reason so much effort has been spent trying to pin down a value for h0. And over the years, estimates have been converging towards about 70 of these, let's call them Hubble units, that's kilometers per second per megaparsec. But cosmology can be a tricky business. By the 1980s, the simple idea of an expanding universe had become a Big Bang model, finely tuned and fragile. And inconsistencies had appeared, like galaxies seeming to be older than the universe. In fact, by 1992, rumours were going round about the death of the Big Bang model. But then cosmologists got their first real taste of this, the cosmic microwave background, or CMB, a signal which saved the Big Bang. Almost every feature in this extremely filtered plot could be made to fit so well with Big Bang expectations that this cosmic microwave background is now seen as a smoking gun, actual proof that the universe began with a hot Big Bang. After all, if this microwave background is not a redshifted surface of last scattering, what else could it be? Well, paper 42, section 4, makes a suggestion that the natural temperature of empty space is not zero. Quote, throughout all organized space, there are organizing electronic energies, end quote. This paragraph, presented in 1934, raises a possibility that the microwave background is not a surface of last scattering from some Big Bang, but simply one of many interesting properties of pervaded space. But hang on, if the cosmic microwave background, this non-zero temperature of space, is not a redshifted surface of last scattering, then what happens to that smoking gun, that signal which saved the Big Bang? Well, for now, putting aside this unorthodox, ambiguous alternative, this cosmic microwave background has allowed cosmologists to build and to polish up a consensus model for native cosmology, so-called lambda CDM. Here, lambda means something like Einstein's cosmological constant. CDM is cold dark matter, and adding a few more bells and whistles, we get this standard model. But just when cosmologists thought they could relax, we got this. Using direct measurements of standard candles like Cepheid variables and supernovae, estimates for H0 have converged to a value somewhere above 73. But as this lower red curve shows, using Big Bang models and the microwave background, estimates have also converged, but to a different value. From observation, astronomers calculate that H0 must be at least 73, but cosmologists, using their best models, require about 67. Two of the most sophisticated, carefully calibrated, checked and rechecked estimates of the central prediction of current consensus cosmology appear to have diverged. Latest results only compound the problem. For cosmologists, this divergence became so unsettling that in July 2019, the folks who run the surveys and write the papers which shape current cosmological ideas got together in Santa Barbara to try to sort things out. Here's a snapshot from the conference. All the big guns were there. Over lunch on the first day, some of the attendees were talking about how to classify levels of disagreement between model predictions. Sylvia Gali from the Planck satellite team compiled this list. The point being that the disagreement between model predictions for H0 is now greater than 5 sigma, which brought to mind a moment from earlier in the day. Things were proceeding as things do at a cosmology conference, when some guy over in the corner, front row, pointed out that in his field, particle physics, when researchers have a discrepancy this big, they declare a crisis. This is David Gross, the director of the institute where the conference was being held. So here we have a couple of, apparently, incompatible predictions from our current best fit model for the history of the universe, prompting one researcher to sum up the situation like this, quote, "It looks like we're going to have to learn something interesting in order to figure this out." As we're about to see, the Urantia Book suggests something interesting, but first a comment. Each of these predictions comes from an attempt to fit data to a lambda CDM hot Big Bang, But if this underlying model is wrong, or not even wrong, then the finely tuned parameters of this model become like epicycles, helping to fit an erroneous model to increasingly inconvenient facts. So what does the Urantia book suggest? It suggests not one, but two large-scale motions of space itself. First, cycles 2 billion years long of gentle oscillation, a periodic expansion and contraction of all space, which the papers call space respiration. And second, the counter-rotation of nested levels of outer space. Okay, but can rotation and gentle oscillation explain the systematic, distance-dependent redshifts that astronomers actually observe? And what about that microwave background? Good questions. Let's see what the Urantia book has to say. And let's begin with Hubble's law. If Hubble's law were true, then this plot says that if we find a galaxy with a redshift of 0.16, then we can simply read a Hubble diagram to find that that galaxy must lie about 2.2 billion light-years away and be receding at about 50,000 kilometers per second. In other words, about 30,000 miles a second, a speed which might sound familiar. From paper 12, section 4.14, quote, "It will appear that these far-distant systems are in flight from this part of the universe at the unbelievable rate of more than 30,000 miles a second." End quote. At the unbelievable rate. What does the Urantia book say about this, quote, unbelievable rate, this apparent speed of recession? But this apparent speed of recession is not real. This statement is not presented as a hypothesis for us to test. It's presented as a fact which the author is in a position to know. They go on to explain that beyond a certain distance, this redshifting of spectral lines becomes, quote, wholly unreliable, end quote, as a method for estimating distance or speed. Which brings us back to those limitations of revelation discussed in paper 101. In section 4, the authors explain that with regard to science and cosmology, they were not free to say too much. Like that prime directive in Star Trek, they were not to interfere. However, they do say that if we're barking up the wrong tree, they can tell us, that's the wrong tree. From paper 101, section 4, quote, "While statements with reference to cosmology are never inspired, such revelations are of immense value in that they, at least transiently, clarify knowledge by." They then list those 5 ways in which this sort of limited revelation can be of, quote, immense value. The first goes like this, quote, Number 1, the reduction of confusion by the authoritative elimination of error. But this apparent speed of recession is not real. Is this a case of number 1, the reduction of confusion by the authoritative elimination of error? As far as I can tell, this question of redshift and Hubble's law is the only place in the papers where the authors tell us that one of our scientific assumptions is wrong. Elsewhere, they either echo prevailing ideas, like that distance to Andromeda, or reveal things beyond human capacity to prove, like ultimatons. But here they point to a particular and critical assumption about Hubble's law and tell us bluntly that it's wrong. So what about those redshifts of distant galaxies? In paper 12, section 4.14, the author claims that beyond a certain distance, other effects begin to overtake speed of recession or radial separation as the primary cause of cosmological redshift. Other effects? What else could be causing a systematic, distance-dependent redshifting of spectral lines? Well, let's take a look. In Big Bang models, an assumption is that redshift is proportional both to distance and to velocity. The further away a galaxy is, the greater its speed of recession, or rate of separation, and thus the greater the redshifting of its spectral lines. So for a galaxy with measured redshift of 0.16, our current Big Bang model, lambda CDM, predicts that that galaxy must be about 2.2 billion light-years away and be receding at a rate of about 30,000 miles a second. But from Einstein, such a rate of recession implies a relativistic shift of 0.16. This convenient match is one of the features of lambda CDM, that with a few nips and tucks it can be made compatible with Einstein's faint glimpse about space and time and gravity. In this sense, this model is said to be a solution of Einstein's equations. But in 1949, a curious character pointed to another, very different solution. The character was Kurt Gödel, and the occasion was Einstein's 70th birthday. What Gödel had noticed was that if the universe were not simply expanding, but also rotating, then funny things would happen to space and time. For example, in a rotating universe, Einstein's equations appear to allow travel backwards in time, so-called closed time-like curves, something that cosmologists tend to dislike. Also, a rotating universe implies some kind of center of rotation, which cosmologists really dislike. So Gödel's curious solution remained, like the man himself, a curiosity. But it did get people thinking. What if the universe were rotating? After all, absolutely everything in the universe either spins or rotates. Why not the universe itself? But if the universe were rotating, and if we were near the center, then once again Einstein has something to say. If that same galaxy, 2.2 billion light-years away, were moving not away from us, but sideways across our line of sight at a relative rate of half the speed of light, then special relativity predicts that we'd measure a redshift of 0.16. Same redshift as predicted by lambda CDM. Speaking about these redshifts, this distortion of spectral lines, in paper 14, section 4, the Urantia Book writes, quote, "But the greatest of all such distortions arises because the vast universes of outer space seem to be revolving." End quote. The claim here is that the main component of the enormous redshifts of quasars and distant galaxies comes not from a runaway expansion, but from rotation. Which brings us to the Urantia Book's unique idea of nested, counter-rotating levels of outer space. The idea is that entire levels of outer space are rotating around our place in space, and thus appearing to move sideways relative to us. In paper 11, section 7, these outer space levels are described as, quote, "curved space paths of lessened resistance to motion, surrounded on all sides by relative motionlessness." End quote. Notice at the inner and outer margins, a space level is thus relatively motionless. So in each space level, we'd expect little or no sideways motion at the edges, rising to some maximum sideways flow midstream. Now, about motion along these curved space paths, it's not so much the motion of galaxies through space, but rather the transverse motion of space itself. which, let's assume, is fast enough to be interesting. Now, let's remind ourselves how, on this sort of cosmic scale, how excruciatingly slow the speed of light becomes. For example, imagine this is a segment of the third outer space level, and that this dot, this tiny little dot, marks the spot 2 billion light-years away where a telescope finds a Milky Way-sized galaxy. Now, pause to consider. It takes light travelling at the speed of light 100,000 years to cross that galaxy. 100,000 years to cross that dot, those few pixels in our best telescope's field of view. What this means is that, given current telescopes and techniques, there's no way for astronomers to detect sideways motion of a galaxy or quasar 2 billion light-years away. Well, there is the nano-lensing of quasar caustic crossings, but not quite yet. As we'll see in a moment, for this galaxy to be going with the flow, cruising along this curved space path, it must be moving across our line of sight at a significant fraction of the speed of light. Now, given this possibility of significant sideways speed, of relativistic transverse velocities, plus cycles of space respiration, then Einstein gives us a surprising but simple explanation for the sort of systematic, distance-dependent redshifting that astronomers see. This slide gives a hint of the idea. And here's an example of how this might be interesting. Imagine astronomers find two identical Type 1a supernovae, one about here and another out here 500 million light-years further out. As before, let's say that relative to us, both are going with the flow, moving sideways at half the speed of light. From this sideways motion, both supernovae get a redshift of 0.16. Each would also get a little extra redshift or blueshift depending on the phase of space respiration. But this second supernova is much more distant than the first, and so would appear dimmer than expected, or rather dimmer than predicted by simple Big Bang models, which might lead cosmologists to propose, well, something like an accelerated expansion due to dark energy. In other words, a lambda CDM, for example. So, given that we can get systematic cosmological redshift from relativistic rotation, then the Urantia Book is revealing how we might replace the old idea of a young Big Bang with space respiration, together with nested, counter-rotating levels of outer space. To help get a feel for this kind of relativistic transverse velocity, think about a single cycle of space respiration, 2 billion years long. For 1 billion years, this entire space level expands. For the next 1 billion years, it contracts. Now consider our target galaxy 2.2 billion light-years away, say somewhere near the midstream flow of this curved space path. At a radius of about 2 billion light-years, we'd have a circumference, once around this ellipse, of about 12 billion light-years, more or less. So if our target galaxy were going with the flow, 2.2 billion light-years away, at half the speed of light, then in 2 billion years, an entire cycle of space respiration, it would only move about 1 billion light-years. So it would take about 12 of these 2 billion-year cycles, or 24 billion years, to go all the way around. Average measured redshift, 0.16. Periodically perturbed by the expansion and contraction of all space. Once again, I should mention this is not the scientific method. This is simply an exploration of unorthodox and ambiguous ideas. But we have to wonder, has astronomy revealed any support for a model like this? Well, as we saw earlier, there is this. Our place in space, this yellow dot here in the middle, appears to be ringed by that flow of galaxies mapped by Brent Tully's group. Here we see supercluster watersheds flowing around the local sheet, which surrounds McCall's Council of Giants, which surrounds us. We're in here near Virgo, our local cluster. Once again, allowing for some confusion about what's actually flowing where, if we think of the local sheet here in the centre as the Urantia Book's first outer space level, then this inferred flow of superclusters might indicate the second. So what about redshifts for all these clusters? And is this consistent with the idea of space respiration? Well, here the plot thickens. All these superclusters are about 200 million light-years away, and all have much the same redshift, about 0.016, which implies that this entire ring is expanding. But here's the intriguing bit. In 1934, the author of Papers 11 and 12 wrote that the current cycle of space respiration is about halfway through its expansion phase. In other words, for the past 500 million years, pervaded space has been expanding. So for this ring of nearby low redshift regions, less than 300 million light-years away, the last 500 million years of continuously accelerating expansion would certainly explain these redshifts and an apparent outwards Hubble flow. And given such an apparent local Hubble flow, it's no wonder that astronomers were led to assume a global Hubble flow. But given that beyond 300 million light-years it's still not possible to detect sideways motion, astronomers and cosmologists alike are stuck with Lemaitre's old assumption and that model, lambda CDM. But this business of redshift from rotation and respiration, plus variations in the permittivity and permeability of space, belongs to a study of the master universe and deserves its own seminar. So for now, let's just say that the Urantia Book's unorthodox idea of space respiration plus relativistic counter-rotating levels of outer space is not inconsistent with what astronomers actually see. So for now, let's return to where we began, in the superuniverse space level, at the dawn of time, when those 7 small teams of ancients of days stepped out into the superuniverse rim of the grand universe wheel to kick-start the adventure of time within the radiated influence of 7 master spirits. Mind over matter, spirit over mind, the first source and his architects watching on.